Hello, this is Bethany Sansing-Helton, your instructor for college algebra. We're going to go through sections R5 and R6 today from your textbook, covering rational equations and radicals. So we're going to go ahead and start with the discussion of domain. So when we deal with radicals and rationals, it's very important to pay attention to domain, because not every value of x will always work in every equation. The domain of an expression, equation, or function are all the real values, not imaginary, not complex, non-real, all the real values of x that work in the equation. So linear equations, a lot of what you've dealt with in the past, everything worked. X could be anything you wanted it to be. So for instance, in 2x plus 5 equals y, there's no limitations on x. It can be anything. So the domain in interval notation goes from negative infinity to positive infinity, meaning x can be anything. Same thing with polynomials. There's no limitations on the domain. But when we get into something that is rational, suddenly a rational equation means that I have an equation with a fraction, and if the variable x is in the denominator of the fraction, then I possibly have an issue, because I know with fractions that the denominator of a fraction can never be 0. This is really important to remember. And why can't it be 0? Well, if you think about fractions, the fraction bar represents division, and I can't divide by 0. That would be like performing magic. If I divide something by 2, I cut it in half. If I divide it by 1, it stays whole. If I divide it by 0, it disappears. It's magic. In the real world, nothing like that can exist, so I can never, ever divide by 0. So I have this limitation in the denominator, that the denominator can't be 0. So what I need to do is I need to figure out what values of x will make the denominator 0. So the easiest way to do that is set the denominator equal to 0, x squared minus 4 equals 0, and I can factor x squared minus 4 into x plus 2 and x minus 2, as you see here. Now, using the zero product property like we talked about in the previous section, I know that that means that if the denominator is 0, x would have to either be 2 or negative 2. So writing this as a domain limitation, I would say this is in set notation here, the set of all x such that x can't be 2 and x can't be negative 2. And it's implied then that x is all other real numbers. With a radical equation, here the radical needs to extend all the way across here, I have y equals the square root of x plus 2. Now, what about this? Are there any limitations here? And yes, there are. The limitations for a square root or a fourth root or a sixth root or any even root is that the number inside of the radical has to be greater than or equal to 0. And why is that? Well, if I have a square root, I'm saying what two numbers multiply together to give me a positive number. And I will never have two if I have a negative number inside the radical, there's no way you can multiply two numbers to get a negative number. The square root of negative 4, you can't multiply 2 times 2 is positive 4. Negative 2 times negative 2 is positive 4. So if I tried to figure out the square root of negative 4, it is not real. And we will actually do those calculations when we get into the complex numbers and imaginary numbers. So this is my limitation. If I want y to be real, then my radicand, the number inside the radical, must be 0 or a positive number. So that means I set everything inside the radical to greater than or equal to 0, and I solve the inequality. So I set x plus 2 greater than or equal to 0. I get x has to be greater than or equal to negative 2. This is an interval notation here, so that means the domain goes from negative 2 to infinity. And it's a square bracket at negative 2 because it's greater than or equal to. Okay, so that's the first thing that we have to look at when we're dealing with rational equations. Here's an example from the textbook. This is number 81 in section R5. The first thing we want to do with equations with fractions is determine the least common denominator. And if I have variables in the denominator, I need to determine the domain. So every single term here has a denominator. There's nothing under this x, so that means I know it's over 1. There's nothing under the 1, so I know it's over 1. So the least common denominator is all the different denominators, common factors multiplied together. So it's 1 times x minus 7, or just plain old x minus 7 is my least common denominator. Now, since x minus 7 is in the denominator, I know that for my domain, I would set x minus 7 equal to 0 to determine the domain, so I know x can't equal 7. And so this will come back when we solve the problem. We just need to make sure that our answer is not 7. Okay, so there's a number of different ways to clear the fractions for these problems. I'm going to go ahead and do it by multiplying the entire equation by the least common denominator. So I'm going to put the whole thing in parentheses, and I'm going to multiply every single term by x minus 7. So when I distribute that x minus 7, I get x minus 7 times x plus the x minus 7's cancel for the second term, so I just get 14, equals 1 times x minus 7, and then again the x minus 7's cancel for the last term, and I get 2x. Okay, so this is the equation I have to solve now. Much simpler to work with because there's no fractions. So let's start by distributing in this first term. I get x times x, which is x squared, x times 7, which is 7x, plus 14, and that equals x minus 7 plus 2x. I'm going to take a look at this problem. Now, since this is an x squared, I want to go ahead, I'm going to change this to red. So since this is squared, I know it's a quadratic. So since it's a quadratic, I know I need to move everything to one side of the equal sign to put it in standard form. So I'm going to move this stuff over here. First, if I combine like terms, x and 2x is 3x, so I have 3x minus 7. But I want to move that stuff to the other side. So I'm going to subtract 3x from both sides. I'm going to add 7 to both sides. So when I do that, I subtract 3x, I add 7, so I get x squared minus 7x minus 3x gives me minus 10x. 14 plus 7 is plus 21, and that equals everything on the right cancels out, and I get 0. So now this is a quadratic. I can tell right away I can solve this by factoring. Two things that multiply to give me a positive 21 and add to give me a negative 10 are a negative 7 and negative 3. So this is x minus 7 times x minus 3. I use the zero product property, set each binomial equal to 0, and then I solve each one. So x minus 7 equals 0, which gives me x equals 7, and x minus 3 equals 0, which gives me x equals 0. I'm sorry, x equals 3. So now I need to verify that my solution is in the domain. Okay, so here's what I'm talking about. We figured out that x can't equal 7 because if it was 7, the denominator of these fractions would be 0. So, but I found here x equals 7. Okay, so what does that mean? That means this isn't really an answer. No, this one will not work. So my solution, I only have one solution to this problem, and it's x equals 3. Now the last thing we want to do is we're going to really verify that this is going to work by substituting it back in. So the left hand side becomes 3 over plus 14 over negative 4, and the right hand side becomes 1 plus 2 times 3 is 6 over negative 4. So 3 plus negative 7 halves, that's negative 3 1/2. So the left hand side is negative 1/2, And then the right-hand side, this is negative 4 over 4. That's 2 over negative 4. That also equals negative 0.5. Now, you can also type these into your calculator. But you want to make sure, especially with rationals, that you go back in and check and make sure they work. Next is simplifying radicals. So to simplify, there's a difference between evaluate and simplify. And it's very important that you recognize this difference. So evaluate means you just plug the numbers into your calculator and you come up with a decimal answer, an approximate answer if necessary. Simplify, you only give exact answers, which means that there will frequently be a radical in your final answer. And the rules for simplifying is that there are as few radicals as possible in the expression, and the radicands, everything inside, is as small as possible. So if we look at this example here, I say, okay, this is a square root, and so I need to figure out how many pairs of numbers I have in here. So I'm going to make a factor tree for 75. 5 has to go into it, so 5 goes into 75. 1, and then 25 is 15, and then 15 breaks down to 5 and 3. So I have a pair of 5s inside this radical. There's a lot of different ways you can do this. If you have a different method, please feel free. But so every pair of numbers comes outside the radical as a single number. So the pair of 5s comes out of the radical as a single 5. There's only one 3, so that has to stay inside. It's trapped. It can only come outside if it's got a partner. Now, x to the 9th is, there's a lot of different ways you can look at this, but we can factor it into x and x to the 8th. So why do I care about x to the 8th? Well, I can make a pair from an even exponent. So I can split up x to the 8th into x to the 4th and x to the 4th. Now again, so many different ways to do this, and I can help you if you need it. So helping you with your special method to do this. So the x to the 4th, I have a pair of x to the 4ths, so they also come outside the radical. I'm going to erase that square root of 3 here and put in the x to the 4th, and then I'll put that back. So the x to the 4th comes outside the radical. All the stuff that didn't have pairs stays inside. So the 3 stays inside and the remaining x stays inside. This is now simplified as much as possible. Again, I can help you with your own special needs if you need it. Just talk to me. Okay, next we're going to rationalize the denominator of a fraction with radicals. So this covers a lot of different aspects of working with radicals all in one problem. And what we're going to do is, what does it mean to rationalize? Well, a rational number is an integer or a fraction, and it does not include radicals, and it does not include imaginary numbers. So if I want the denominator to be a rational number, that means I have to get rid of the radical. Now, because I have a radical plus something, the only way to get rid of the radical is to multiply by something called its conjugate. So the conjugate is going to be the same thing with the minus sign in between the two numbers. And I can multiply anything I want by something as long as it's equivalent to 1. So since I multiplied the denominator by the square root of 3 minus 1, I also have to multiply the numerator by the square root of 3 minus 1, because this new fraction that I created is equivalent to 1. So I can always do that. Now I have to go ahead and FOIL the numerator. Hopefully I have space to do this. Well, I'll write it below it. So I take the first term, 5 square root of 3 times the square root of 3. Square root of 3 times the square root of 3 gives me the square root of 9, or just 3 because I have two square roots of 3 multiplying by each other, the radical is canceled out. So when I multiply the first two together, I get 5 times 3. I multiply the outsides together, I get minus 5 square root of 3. Multiply the insides together, I get minus 2 square root of 3. And I multiply the last terms together, I get 2. That's my numerator. My denominator is a difference of squares. I take the first terms multiplied together, and that ends up squaring them. The square of the square root of 3 is 3, and so the denominator is 3 minus 1. So now I need to combine like terms. 5 times 3 is 15. Helps sometimes I just write it above it. So 5 times 3 is 15. 15 plus 2 is 17. And then these two terms, you can treat a radical like a variable. As long as the radical exactly matches, then these are like terms. So since this is the square root of 3 and this is the square root of 3, I could pretend that these were x's. If I had minus 5x minus 2x, I would say minus 7x. So this is minus 7, and then my variable is my radical. It's not x, it's the square root of 3. So the numerator is 17 minus 7 times the square root of 3. The denominator, 3 minus 1, is 2. If I could simplify this more by dividing the numerator by the denominator, I would. But since both numerator terms are odd and the denominator is even, I can't do anything else with this problem, and I'm done. Next we come to rational exponents. Now, a little bit about roots and powers, as I mentioned already. Roots undo powers. So if I had x cubed and I wanted x to the first, I would take the cube root to get x to the first, because the cube root undoes the cube power. So let's look at a different way. What if I just looked at the exponents here? I would say 3 times what would give me a first power? Well, I know that 3 times 1/3 is equal to 1. So what does this tell us? Since I know that if I have a cube root and a cube, I get a first power, that must mean that my cube root is actually a fractional exponent. This is a rational exponent. This is what we call a rational exponent if it's a fraction. And you can always write radicals as fractional exponents. In general, if I have a radical and the index of the radical, the n is called the index. Sometimes it's also got another name that is escaping me right at this second. If the index is n and the power of the number inside or variable inside is m, you could also write it as fractional exponents where the power is the numerator and the index is the denominator. So let's look at 8 to the 2/3. So we're starting over here, 8 to the 2/3. Now first of all, because of what I know about fractions, I know that 8 with the 2 over 3 is the same as 8 raised to the 2 times 1/3. So I could write it as 8 squared raised to the 1/3 power. That would give me 2 times 1/3 because we multiply exponents when we're raising stuff to a power. Or I could also, since in multiplication order doesn't matter, I could raise it to the 1/3 first and then have it times 2. And then taking this idea that the fractional exponent is really radical, I could write it as a radical. So I could say the cube root of 8 squared, or I could say the cube root of 8 all squared. So this I could calculate, right? What's the cube root of 8? What 3 things multiplied together to give me 8? Give me 8. It's 2. So the cube root of 8 is 2, and 2 squared is 4. So 8 to the 2/3 you can do without a calculator, and I would expect you to be able to do that without a calculator, and the answer is 4. Again, remember, the power is the numerator of the fraction, and the denominator of the fraction is the index of the radical. Let's do a little bit harder example, 27 raised to the 4/3. So in general, we do the denominator part first. We do the radical first because it makes the number smaller which is then easier to raise to a power. So I'm going to take the 27, so it's the cube root of 27 raised to the 4th power. So if I break down 27, 27 is 9 and 3, 3 and 3. So I have 3 3's in there. So the cube root of 27 is 3. And so I just need to know what 3 raised to the 4th power is. 3 times 3 is 9. Times 3 is 27. Times 3 is 81. So 27 raised to the 4/3 power, is 81. All right, finally, another type of problem you'll see that requires you to know your laws of exponents is something like this, where I have fractional exponents, and you could even have a negative exponent in here. You're going to need to go ahead and review those on your own if you don't remember if you don't remember your laws of exponents. So y to the 1/5 over y to the 9/10. Now, my rules of exponents, I know if I have the same base, the base here is y. This is referred to as our base. So if they as long as they have the same base, and I'm dividing the numbers, that's the same as subtracting the exponents. So 1/5 minus 9/10. I can subtract the exponents by creating common denominators. So I would change 1/5 to 2/10, as you can see here. 2/10 minus 9/10 is a negative 7/10. But if it's simplified, you never leave a negative in the exponent if you're simplifying. So the last step is to make it a positive exponent, and we do that by moving the entire thing to the bottom of a fraction bar, changing the exponent to positive. If you need more review on this, please come talk to me and I will guide you, give you practice handouts or suggestions. Okay, now let's look at single radical equations. Now it's really important to always isolate the radical on one side of the equal sign first. This is always your first step. And then you also need to determine the domain so you know what values of x will be allowed for your solution. Now, I like to, the example I like to give my students is pretend that the radical is your friend. So this is my buddy, square root of 3x minus 5, and I'm trying to solve this problem. I'm trying to, my buddy is square root of 3x minus 5. I'm trying to figure out what x is. I'm trying to help my friend solve their problem. So when I have a friend that's got serious problems, I always try and go and talk to them by themselves to help them work it out. So I isolate my friend. So in the same way, I'm going to isolate the radical. So first thing I'm going to do is I'm going to move the 5 to the other side of the equal sign. So I get negative 3 square root 3x minus 5, here's my radical, equals negative 9. Now a radical can't equal a negative number, but don't worry because we still have to clear this coefficient. So I'm going to go ahead and change the color of my pen so it's clear that I'm doing another step. I divide both sides of my equation by negative 3. So when I do that, I get the square root all by itself. I have now isolated my friend and I am more able to help them solve their problem. Now I make sure that the radical equals a positive number, which it does, and then I check the domain. So the domain requirement is that the radicand, the stuff inside, is greater than or equal to 0. So I solve this linear inequality and I get that x must be greater than or equal to 5 over 3. Okay, so we just need to keep that in mind for when we finish this problem. So the next thing that we have to do is we have to clear the radical. Now remember, roots undo powers. For example, if I look over here at this very simple example, if I had the square root of x equals 4, and I want to know what x is, I would square both sides to get rid of the power, and I would get x equals 4 squared, or 16. So we do that same thing here with this more complicated problem. I square the left-hand side, and as long as I do the same thing on the right-hand side, my equation stays balanced. So I get 3x minus 5 equals 9. I solve for x now. I get 3x equals 14. Divide both sides by 3. I get x equals 14 over 3. Now, is this greater than 5/3? Yes. Fantastic. The final step would be to go and plug this number into the equation and make sure that it really does equal -4. So we're going to check it. 14/3 times 3 is 14. Does this equal -4? Well, 14 minus 5 is 9. Square root of 9 is 3. So I get 5 minus 9, which does indeed equal -4. Fantastic. Okay, so sometimes you have problems like this where you have two radicals in the problem, and people say, well, how do I isolate the radical here? And what you need to do in this case is go ahead and get the more complicated radical all by itself. So the one with the addition is more complicated, so I'm going to move the square root of 24x to the other side of the equal sign. Don't worry about simplifying that radical at this point because we're going to clear it. So I get the square root of 12x plus 9 is equal to -3. Well, actually, let's go ahead and put the square root first here. The square root of 24x minus 3. Okay, so now what I need to do is, just like last time, I need to square both sides of my equation. So I square the left-hand side and I square the right-hand side. Now the left-hand side is really easy. The radical is cleared. But the right-hand side, you cannot distribute an exponent if there's addition or subtraction in the problem. So what we have to do is remember that squaring something means that I am actually doing repeated multiplication, so I need to FOIL it. So I have the square root of 24x minus 3 times the square root of 24x minus 3. Now remember, when I multiply radicals together, if they're exactly the same, two radicals cancel out, so I get 24x minus 3 times the square root of 24x, that's the outside, minus 3 times the square root of 24x, that's the inside, plus 9. Okay, so now I want to get my radical all by itself again. So I'm going to move the 24x to the left-hand side. And I'm going to move the 9 to the left-hand side. Sometimes it helps to put a little line between them. And so when I do that, the 9's cancel out on both sides, and I get a negative 12x equals, my 24x cancels over here. I combine like terms here. I get negative 6 times the square root of 24x. Okay, so let's go ahead and change the color of the pen again and divide by negative 6. So the left-hand side becomes 2x. The right-hand side becomes the square root of 24x. So now I've isolated my radical again. So when we have more than one radical, we just end up doing repeating the process more than once. So now I'm going to go ahead and square both sides again. So I square to clear the radical. So I get 4x squared equals 24x. This is a quadratic, so I need to move everything to one side of the equal sign and factor. 4x squared minus 24x equals 0. Let me come back up here. I factor. My greatest common factor is 4x, and I get x minus 6 equals 0. So I have two answers. I get 4x equals 0, or I get x minus 6 equals 0. So when I solve these, I find that x could be 0, or I find that x could be 6. Now, I forgot to do the domain. So when I do the domain question, I need to make sure these will work in the domain. Now you can just, there's two options. You can just test each of these inside and make sure they both work, or you can calculate the domain as well. I'm going to test them both, but let's just check what the domain is for 12x plus 9. Remember, 12x plus 9 must be greater than or equal to 0, so that means x is greater than or equal to negative 9/12, which is the same as negative 3/4. So both of those are greater than or equal to negative 3/4, and for the 24x, that just has to be greater than or equal to 0. So they work in the domain. Now let's just check and make sure they really work in the problem. So let's check x equals 0. So x equals 0 gives me the square root of 9 minus 0. Does that equal negative 3? Oh man, look at that, it doesn't. 3 equals negative 3. Okay, so that doesn't work. Now let's check x equals 6. So when I do 6, 12 times 6 is 72 plus 9. So that's the square root of 81 minus the square root of 6 times 24, which is the same as 12 times 12. So that's 144. So the square root of 81 is 9. The square root of 144 is 12. That one does work. So this is the funny thing about two radicals, is that even though your answer works in the domain, it might not work in the problem when you go back and check it. And you didn't do anything wrong. It's just the way it is. So you always, always, always need to check your answers for these multiple radicals equations. Okay, we're almost done. Sorry, this is so long. These examples take a long time to go through. Radical and rational exponents. Now again, this is just a reminder. If I can rewrite something with a radical as a rational exponent. So why is that useful? Well, look at this problem here. This has a mixture of radical and rational exponents, which isn't helpful. You need to make them both the same. You can make them both radicals, or you can make them both rational exponents. Now I'm going to make them both rational exponents. And when I do that, I see that these are actually like terms on the left-hand side. So I combine like terms. 1x to the 2/3 minus 2x to the 2/3 is negative 1x to the 2/3, and that equals negative 4. Now, if I want to change the signs in the problem, it's easy enough to do. I multiply the entire problem by negative 1, which just changes both signs. So now I get x to the 2/3 is equal to 4. How do I clear this? Remember, I want x to the first power. So if I multiply 2/3 by its reciprocal, I will get 1. So I need to raise the 2/3 to the 3/2. So I need to raise 4 to the 3/2. So I get x equals, if I change the 3/2 to a radical, it's the square root of 4 cubed. Square root of 4 is 2. 2 cubed is 8. So I get x equals 8. Finally, we get rational exponents that are quadratic in form. Why is this quadratic in form? Well, take a look at the middle term and notice that it's a 1/3 power. And then take a look at the power on the first term. If I square this middle term and get the first term, that's a good sign that I have something quadratic in form, and this is how I decide what my u is. U is always going to be the piece of the middle term that I have to square to get the first term. So when I rewrite this using u substitution, I get u squared minus 2u minus 15 equals 0. So then when I go ahead and factor that, two things that multiply to give me negative 15 and add to give me negative 2 are negative 5 and positive 3. So I get u equals 5 and u equals negative 3. Again, I don't care what u is. I want to know what x is. So I get x to the 1/3 equals 5, and I get x to the 1/3 equals negative 3. So if I want to figure out what x is, hopefully you are ahead of me on this one. What do? I cube both sides. So for both of these problems, I cube it, so I get x equals 5 cubed, which is 125, and I get x equals negative 3 cubed, which is negative 27. So two answers. If you were to write it in set notation, you could just write the two numbers inside curly brackets with a comma in between them. All right, last slide. The Pythagorean theorem. Hopefully this is just a quick review for you and you're like, oh, I know what this is. The Pythagorean theorem can only be used with right triangles. That means a triangle that has a right angle. Bad drawing. A right angle is signified with a little box. The side opposite the right angle is always the longest side. It's called the hypotenuse. It always uses the letter C. The other two sides, it doesn't matter which one you let be A and which one you let be B, just so long as they're both there. And we use this formula, a squared plus b squared equals c squared. So for example, I have a radio tower. It's secured by cables that are anchored in the ground 8 meters from its base. If the cables are attached to the tower 24 meters above the ground, what is the length of each cable? So I have a radio tower. Here's my tower. It's 8 meters from the base is where they anchor. So if I go, I lost my pen. Here it is. So if I draw a line and I go out 8 meters, that's where my cables are anchored. And then not necessarily the top of the tower, somewhere on the tower, 24 meters up the tower, I have where the cables start. And I want to know what this side is. So in real world problems, anything standing up, a building, a tree, you, we all make right angles to the ground. So this is a right triangle. The side opposite the right angle is always the letter C. So all I do is plug this into the Pythagorean theorem. 24 squared plus 8 squared equals c squared. So I go ahead and do those calculations and I figure out an exact form and an approximate form. So in order to do this, I need to get a calculator. So plugging it into my calculator, 24 squared plus 8 squared is 640, and that equals c squared. If I want to know what c is, again, I undo squaring by taking the square root of both sides. So normally when you take the square root of both sides, you get plus or minus. But this is a length. Lengths are never negative. So the square root of 640, that's 64 times 10. And I know 64 is a perfect square. That's 8 times 8. 10 is 2 times 5. There's no pairs there. So in exact form, part A, the answer to part A is going to be 8 times the square root of 10 meters. The approximate form, rounding to 1 decimal place, we have to use a calculator again and figure out the square root of 640. And it's 25.298 is the approximate square root. So it says rounding to 1 decimal place. 25.298. If I round it to one decimal place, that's about 0.3. So it's about 25.3 meters long. So there you go. I hope you enjoyed this, and I look forward to doing the practice with you in class today.